Greetings. We begin a new unit today, the 7th unit of this course on atomic photoionization, and we will begin to see the applications of the quantum mechanics that we have developed in earlier units, and they will all come together when we get into these applications. And I will introduce you to photoionization cross sections, angular distributions of photoelectrons, and some of the other properties. So, this is the experiment that really contributed a lot to quantum mechanics, because it was the interpretation of this which really led to the understanding of the quantization of the electromagnetic field. And so, this was a fantastic experiment done by Hertz and Leonard, and its explanation in 1905 by Einstein is what led to the formulation of quantum mechanics. So, you have these photoelectrons coming out from this metal plate when light falls on it, and in the high school, when you study about this experiment and about quantization of energy, you only look at the energy consideration, that there is a conservation of energy, and the kinetic energy of the photoelectrons is just a statement of conservation of energy. From the photon energy you remove the binding energy and you get the kinetic energy, right. But there is so much more to this experiment, because a physicist likes to do a complete experiment, as get maximum information about the system which is being investigated. So, I will talk about the complete experiment and how it is interpreted in the context of quantum mechanics. And you have this transition from a bound state, when a photon is absorbed, the electron goes into the continuum, and this transition is affected because of a certain interaction between the electromagnetic field and the quantum atomic system. So, this matrix element that you see over here is what measures, what gives us a measure of the probability amplitude for transition from an initial state to a final state. The modulus square of this will give the transition probability, and it will be proportional to the intensity of absorption. So, the photo absorption cross section and so on will be related to this. So, a number of questions come up. How do you describe the initial state? Is it a non-relativistic initial state? Is it a relativistic initial state? Does it take into account correlations? Does it take into account the exchange correlations? Does it also take into account the Coulomb correlations? So, there are a large number of questions which can be raised on what this initial state is, and at the simplest level it can be like a hydrogenic state, but then there are very many complex levels at which this question can be answered, and to get a really good answer, one has to do a fully relativistic many body formulation of quantum mechanics, apply to atom, but get correlated wave functions for this to describe the initial state. Then you can also ask, how do you describe the coupling operator which is responsible for effecting the transition, because there is an interaction between the electromagnetic field, and if you express the electromagnetic field as like e to the I k dot r, you have got the vector potential, then you can expand this in multipoles. And do you take into account all the multipoles, or do you take only the leading term? Do you take the dipole term? Do you take the quadrupole term? Do you take the octopole term? So what exactly is the coupling? And again, you can make a number of approximations and deal with this operator T, which is responsible for effecting the transition. And then the question is, how do you describe the final state wave function? And here again, depending on the level at which you are answering this question, you have a multiplicity of alternatives to consider. At the simplest levels, this can be continuum non-relativistic wave function, it can be relativistic continuum functions. Then again, you can take into account the correlations and interchannel coupling in the continuum, so to get more exact answers. So again, there is a very complexity of levels, and very detailed investigation of this matrix element certainly requires a very thorough analysis of the quantum many body problem of the atomic system. Now, what we have learnt in the previous unit is that the final state wave function is a free particle solution as such, and it has to be described according to the ingoing wave boundary condition. So, at the non-relativistic level we know what a wave function looks like subjected to ingoing wave boundary condition, and that is the solution which I have written over here, and it is precisely this form which you must use in this matrix element, otherwise you will not get the right answers. If you use psi f without going wave boundary conditions, you will not get the correct answers for the photoionization problem. So, that is the reason that I discussed the ingoing wave boundary conditions before we came to this topic. So, these are very powerful tools to study atomic systems, ions, also negative ions, not only positive ions. When you have a negative ion, you know, when it absorbs energy, the extra electron which is attached in a negative ion can get detached, and that process is called as photo detachment, and you would carry out similar studies on molecules as well, and clusters and surfaces. So, it becomes a very powerful tool in surface analysis. So, which is why the subject is of considerable importance and interest. So, you have a continuum of energies, and these are the photoionization transitions that we shall be talking about. So, basically if you have a coordinate system, a Cartesian coordinate system, and you have got incidence of electromagnetic energy along the z axis, and so you choose your z axis along the direction of incidence of the electromagnetic energy, and let us say a photoelectron, the electron which is knocked out is what I shall refer to as a photoelectron. So, this is the photoelectron which comes out, it comes out in a given direction. The exit channel is unique in the photoionization experiment, as we know. So, this is the direction, let us say it goes out in the direction with a wave vector k, and this is the direction of ejection, and with reference to the polar axis z, this angle is theta. Then there is an azimuthal angle phi with respect to x axis, and we choose the x axis to be the direction of polarization of the electric intensity. So, that will be the reference scheme, and our goal is to obtain expressions for the photoionization cross section and the and the angular distribution, because with reference to the direction of incidence of the photon and with the reference to its polarization direction, what is the angle at which this electron comes out. So, that is the question which we shall take up, and that is called as the angular distribution of the photoelectrons. So, in addition to the cross sections and the angular distributions, you can also measure the spin polarization parameters of the photoelectrons. So, these are like compatible measurements with each other. So, the uncertainty principle will allow you to carry out these measurements, and which is why a complete experiment requires you to study all of these parameters, not just one of those. So, I mentioned earlier that you have the coupling operator to be either the dipole or the quadrupole, or it could be any other, and that again sets a level of approximation on the scheme that you are implementing. So, you can do the initial state, as I mentioned, at the independent particle approximation at the Hartree-Fock level. If you do a relativistic self consistent field, you have got the Dirac-Fock wave functions to describe the initial state. If you take into account the electron correlations, for which you will need a multi-configurational Hartree-Fock MCHF or a relativistic self consistent field, but to take into account the correlations which you have ignored in the Hartree-Fock at the Dirac-Fock level, which we discussed in the earlier unit. So, if you want to include those, then you will have the multi-configurational Hartree-Fock or the multi-configurational Dirac-Fock. So, that is the MCDF, and you can describe the initial state at a variety of approximations and a variety of accuracies that you can go for, and then you can also take into account the configuration interactions in the continuum. So, that will give you the correlations in the final state as well. So, let me give you an example over here. Let us take an atomic system like the magnesium atom. Its atomic number is 12, and there are this is the electron configuration in the ground state, in the usual ground state of magnesium. And if you just consider the photoionization of the outermost 3s electrons, then relativistically this outer electron can go to a continuum p 3/2 orbital and also to a p 1/2 orbital. So, there are two possibilities, and this is again like a Young's double slit experiment, that there are two possibilities and you will therefore expect to see some interference effects. Okay. So, when you take into account these interference effects, you say that you have taken into account the configuration interactions between these two possibilities. There are these two configurations, one leading to a p 1/2 continuum state, the other leading to a continuum p 3/2 continuum state, and you can take into account the interference between this. This is the interchannel coupling between these two channels. This transition is affected by E1, which is the symbol for the dipole transition, and I have mentioned the dipole transitions earlier. So, the dipole transitions have the selection rules delta L equal to plus or minus 1. So, you have got a transition from S to P, which is permissible under the dipole selection rules, but then you may have, as I mentioned, not just the dipole transitions, you may also have the quadrupole transitions, and the selection rules for the quadrupole of course are different. So, if you have a quadrupole transition which is represented by E2, then delta L can actually be 2. So, you can have a transition from S to D. So, you will have two relativistic transitions, S to D 5/2 and S to D 3/2. So, again depending on what is the coupling operator you are making use of, you would have either the dipole calculations or the quadrupole calculations, right. And the atomic system, when it responds to the electromagnetic energy, it is going to respond in its natural way. So, strictly speaking, you really need to include all the operators, all the coupling to get the exact picture, but you can get a fairly good description of the process by making some approximation. So, that really depends on what is the accuracy of your measurement process and in how many details you want to go. But now very sophisticated experiments can be done, very high precision electronics is available, very powerful light sources are available. So, you also need very rigorous theories to explain these phenomena, which is why you need relativistic quantum many body theories to explain these processes. So, sometimes you have a transition just to the discrete level, and that is photo excitation. But at the energy at which you have got excitation from one state, from a less bound state, you could also have ionization, and then you can have interference between ionization and excitation also. So, that leads to some very interesting phenomena such as autoionization resonances, and I will mention some of these in the later part. So, you measure what is called as the cross section, which is actually transition probability, okay. And transition probability, it is scaled according to certain relationships, I will explain this. And then the usual measure for the transition probability is in terms of what is called as a cross section. You also measure for the complete measurements, for the complete experiment, the angular distributions of the photoelectrons, and this is described by a number of parameters. So, if you have the dipole approximation, you have only the beta parameter, but if you also include the quadrupole parameter, you have some additional parameters like gamma, zeta, and so on. And then along with the measurements of the spin polarization parameters, you get a complete experiment and a complete description of the photoionization process. So, our goal in this unit is to describe the tools that we need to explain what photoionization cross section is and get its exact description. The terminology also makes use of certain classical models, because very often some of these classical ideas are used in the description of the quantum phenomena, but then our goal is to have a fully quantum mechanical model, and it is therefore useful to begin with the classical model and then go through these steps so that we do not miss out, and we will then be well equipped to describe this process comprehensively. So, essentially we are describing the interaction of electromagnetic radiation with an atom, and the classical model presumes that the electrons, as in response to the electromagnetic energy, they oscillate about a certain mean position. Now, we know that this picture is very classical, and from the quantum mechanical point of view it is not correct, but a lot of terminology which gets carried on into quantum mechanics comes from this description, which is why I need to go through it. So, the idea here is that the electrons oscillate about a certain mean position in the atomic system, and as a result of which there is an induced dipole moment, because you have got a charge which is oscillating, right. So, you have got an induced dipole moment which is sets in, and you will therefore expect to meet ideas like atomic polarizability, polarization, susceptibility, and some of these macroscopic electromagnetic properties are then related to photoabsorption cross section. So, through this connection. So, we will develop all the necessary building blocks for this process. So, we will define what is called as the oscillator strength. Okay. The term oscillator strength comes from these oscillations which I already mentioned. So, I will define it rigorously, and this will be related to the quantum mechanical transition probability and then to the cross section, which is the common parameter in terms of which the transition probability is measured. So, we will need all of these tools: quantum mechanics, relativistic effects, many body effects, multipole transitions, all of this will come together, but we will build the model from the ground up, so that we know where the term oscillator strength comes from and how it connects to the quantum mechanical cross section. First principles is from ground up, means so we do not make too many assumptions. We state our postulates from the very beginning, so that we do not have to make too many assumptions. So, we begin with first principles and build on that in a logical way, so that there will be no gaps in our understanding. So, that is the idea. So, you have an electromagnetic field whose electric intensity vector is described by this vector here, which is E0 e to the minus I omega t with a certain phase factor. Let us say the electron's charge is E. A classic reference for this is a review by Fano and Cooper in 1968, which I have referred to. I will also have it uploaded on the course web page. It is a very good paper which describes this phenomenon. And since our model is one of oscillations affected by this, you presume that the motion is described. This is the classical picture, which is mass times acceleration. So, this is essentially the Newton's law that we have written over here, and there is a restoring force. So, there is a certain restoring spring constant which is k, and this is the simple harmonic oscillator of our model, wherein the oscillations are set in by the electromagnetic field. Now, you may consider damping as well, and you know what damping is. So, damping of course is a result of energy loss. It results in energy loss, and one needs to know why there is an energy loss, because all the electromagnetic phenomena are basically conservative interactions, and that is the only interaction to consider. So, why should there be an energy loss at all? So, the energy loss actually comes only because when you set up your equation of motion, you may not have taken into account in your equation of motion all the degrees of freedom. So, there will be some unspecified degrees of freedom due to which there is damping, and that will give you a force which is proportional to the velocity, and then there is a damping coefficient which is twice omega. So, this is the usual classical description of damping, and then you have this damped oscillator driven by this external field. So, you have got this natural restoring force minus kr, there is this damping force, and then there is this driving force. So, this is the equation of motion to a damped driven classical oscillator. Okay. And this is the equation of motion which we need to solve, and you would have done this in your classical mechanics course or in electromagnetic theory. So, a number of different courses you meet this equation, and if you divide by the mass, you get this equation for the position vector, and it has got a solution which is well known. So, this is the solution, you can easily check it out, you can get the velocity, you can get the acceleration, plug it in and see for yourself very quickly. So, this is something that you would have done in your undergraduate courses as well. So, this is the usual solution to the damped driven classical oscillator. So, here omega is the frequency of the driving force and omega 0 comma s is the natural frequency of the oscillator. So, those are the two frequencies that we are concerned with at this point. There is this damping coefficient gamma, and you can easily see that this displacement of the electron goes to 0 as E0 goes to 0. So, essentially we are talking about an induced effect. So, we are talking about an induced dipole moment. Okay. So, this induction is on account of the driving force, which is why it is appropriate to talk about induced oscillating dipole moments, and this is the description that we get from classical oscillator. So, this oscillator strength is what we need to be subsequently connected to the quantum mechanical transition probability and the photoionization cross section, because when experimentalists talk about photoionization cross section, they will always talk about how much oscillator strength is there under the photoionization curve, and that is where you really need to understand the term oscillator strength. So, that is part of the reason that we need to spend some time discussing this classical model. So, these are the connections that we want to establish between oscillator strengths, atomic polarizabilities and the photoionization cross section. So, let me use the definition of atomic polarizability. So, what is this? This is the induced dipole moment per unit electric field, right. So, you have got a dipole moment, you divide it by the electric field which causes it. So, the dipole moment is proportional to the electric intensity, and the proportionality is given by what we call as the atomic polarizability. Now, we also know that the dipole moment is charge times displacement E into R. So, these two are related, they both describe the dipole moment. So, you can get alpha as the ratio of ER over E, right. So, you get alpha, the atomic polarizability, as the ratio of the dipole moment to the electric intensity, and this electric intensity you already know is the modulus of this applied electric field, and the solution R is what we just obtained from the classical oscillator, which is the damped driven oscillator. So, the solution for R we already have with us. So, we plug in this solution for R multiplied by this charge E and divided by the electric intensity. So, this gives us the atomic polarizability. So, now there is E square, there are two places where the electric charge comes. So, you get E square over m, and if you take this modulus and divide it by this term over here, you get omega 0 square minus omega square minus I gamma. So, this is a complex number. Okay. All right. Now, in this complex number you have got omega 0 square minus omega square. So, this is like a square minus b square, you can factor it as a plus b into a minus b and factor out this omega 0 plus omega as a common term. So, over here you have got omega 0 minus omega, but this term must be divided by omega 0 plus omega. Okay. So, I have only factored out this omega 0 plus omega outside, but then the transitions take place at a frequency which is closest to the natural frequency. So, omega and omega 0 s are very close to each other within a certain width. and you can therefore represent this sum as twice the natural frequency, because the sum of these two frequencies is hardly different from twice the natural frequency, but the difference of course you cannot ignore over here, because what you are ignoring is a small number compared to a large number. You cannot ignore a small number when you compare it with 0. So, here you retain the difference omega 0 minus omega, but over here outside I have replaced this omega 0 plus omega as twice omega 0, which is twice the natural frequency. So, this gives me a fairly good approximation to the atomic polarizability, and if you just take this m cross multiply by m and e square, you get this term which is very similar in its form to the solution to the displacement for the driven and damped oscillator. Okay. So, if you look at the similarity between these two forms, you can expect to write the displacement in terms of the polarizability, okay, by factoring out the common terms, because it has almost the same form, and you write the displacement vector in terms of the polarizability, and this turns out to be E over m. This is the direction of the polarization vector, this is the frequency dependent polarizability, which is a complex number as we have seen. Then there is this m over e square which is coming from here, and then of course you have got the driving term. So, this is the solution to the displacement in terms of the atomic polarizability. So, what is the dipole moment? It is just the charge times displacement. So, you multiply it by this. So, this E cancels this E and you have got the rest of the terms here. There is an E in the denominator here. So, this is what gives you the dipole moment, and now we ask what is the average power which is pumped into the atomic system by the electromagnetic field, and intuitively you should begin to expect that this will be related to the photoionization cross section, okay, because our quantum mechanical object of interest is the transition probability, okay, and that will be related to how much power is pumped into the atomic system by the electromagnetic field. Okay. So, we first get a description of this quantity in terms of classical terms, and classically this will be just the average of the rate of doing work, right. So, if you dw by dt is the rate of doing work, you integrate this over time and divide it by the periodic time. So, that is the corresponding to the frequency of oscillation. So, this will give you the average power over one period of the oscillation that an electromagnetic energy is pumped into the system, and this is of course a real quantity because physically you are dealing with real numbers. So, this is the quantity that you want to get. F dot dr is the work done. So, power is just the rate of change of the work done. So, dw by dt is what you want to get, and if you divide F by E and multiplied this by E, you have got dr by dt. So, you get F over E dot E times velocity, okay. That is the term that you have to get, and we have got these expressions from our classical oscillator. So, these quantities, the way we have dealt with them are complex quantities. We are of course interested only in the real part which goes into the physical process, because power is a real physical quantity. So, we will deal with the real parts. So, this dot product that we have to work with, F over E dot E R dot, you really need to take the dot product of the corresponding real parts, and that will give you the physical power which is pumped in of interest. So, let us get this expression and evaluate it, because we already have got expressions for the dipole moment, we also have got the expression for the force. So, now F over E is this quantity here, this is the electric intensity, this is the force per unit charge. We need the real part, which will be the cosine part of this, because the exponential function has got both the cosine and the sine part. The sine part comes with the imaginary I, right. So, you take the e to the minus I theta and e to the plus I theta and divide it by 2. So, you will get half the cosine term. So, this is the real part of the force per unit charge, and likewise you need the real part of the dipole moment. So, here again you do the same thing and you have the dipole moment which you had earlier described in terms of the complex atomic polarizability. You take this complex number, multiply, add to it, sorry, not multiply, but add to it the complex conjugate and then divide by 2. So, that will give you the real part of the dipole moment. Okay. So, now you have got all the quantities of interest, and now you just have to take the dot product of these two quantities. So, let us do that. You take the dot product of these two quantities in the integrand. So, it is a dot product of this quantity here, which is the real part of force per unit charge, this is the real part of the dipole moment, dot it out epsilon dot epsilon, these are unit vectors that will give you unity, and then you have got this term into this term, which will give you e to the minus twice this phase angle. When you take the product of this term and this term, the e to the minus I theta and e to the plus I theta will cancel. So, you get I times alpha star omega. So, likewise you will have minus I times alpha omega coming from here, from these two terms, and then again from the last two terms you get from this term and this term you get a plus twice I the phase, right. So, now we will be interested in carrying out observations over long intervals of time, and we should ask what is it that this will lead to over as we integrate this quantity over large intervals of time. So, what is the integral of this e to the minus I 2 phase factor here, because this is the only time dependent function which is coming here, right. So, over integrals over time, the integration of course has to be carried out from the instant that photo absorption takes place. So, integration is from 0 to infinity, let us say for large time I will say t tending to infinity. So, your integration range is from 0 to infinity, but mind you all of these quantities are multiplied by E0, but E0 was 0 before t equal to 0, right, there was no electric field which was applied. So, without any loss of generality I can extend the range of integration from minus infinity to plus infinity, giving me the same result, because you are adding a number of zeros to the result. So, it really does not matter, but the advantage is that by extending the range of integration from minus infinity to plus infinity, you recognize that you get a delta function. Okay. So, that gives you a very simple result, and the delta function whose argument is the frequency will contribute to the integrals only when omega is equal to 0, and omega equal to 0 corresponds to no oscillation, right. So, that is not going to contribute anything to the oscillatory part at all. So, the quantities of interest therefore, which we will be concerned with are those which are inside these red boxes, because these will make no contribution to the physical phenomenon in which we are interested. So, mathematically you get these terms, these oscillatory terms, but they are of no interest for the physical processing of this information. So, you have got only these two terms in these red boxes. So, those are the ones which I have written here, and alpha is some complex number. So, you have got I times alpha star, and you have to subtract from that minus I times alpha, which is the complex conjugate of this. So, essentially what you get when you do this summation is twice the imaginary part of alpha. Okay. What does it mean? We really arrive at an extremely simple but a very important result, which is the following, that the average power which is pumped into the atomic system by the electromagnetic field is given by omega E0 square by 2. You remember where this omega E0 square by 2 is coming from, it is coming from here. Okay, this is omega E 0 square by 4, but then there is a twice imaginary part of alpha. So, this 2 and this 1 over 4 is what gives you the 1 over 2. So, omega E 0 square by 2 is what you get, times the imaginary part of the complex atomic polarizability. Okay. And this is a result which you will find in Fano and Cooper's paper, you will find it in Fano and Rao's book, and in a lot of literature on atomic photoabsorption processes, in which they will relate the photoionization cross section and tell you that it is a measure of the imaginary part of the atomic polarizability, and this is the connection which I wanted to establish in today's class. So, it is essentially a classical model that I wanted to discuss today, and in the next class I will introduce the quantum mechanical treatment. So, I will of course be defining what is called as the oscillator strength in a rigorous manner, but that is something I will do in the next class. So, if there are any questions, I will be happy to take. Yes, on any part of the class. If none, thank you very much.